Hello everyone, here's the part 3 of our chapter 14 and we're going to learn about the area under the peak here. That is also called the integration or the relative number of protons. Now we have this molecule. There's two regions or two signals. There are two hydrogens would be at the same environment, and there's going to be 9 hydrogens on the same environment. Okay. So the area under the peaks, so this is the integration. So it is given as a ratio of 1.6 to 7. The area under each signal is proportional to the number of protons that produce the signal. So 1.6 to 7 is approximate to 2 to 9 ratio. These compounds also show the same integral ratio. So there is 1 hydrogen here and 3 hydrogens there. So the ratio of protons would be 1 to 3 for this molecule. And similarly, if this is a different molecule, there are 2 hydrogens here and 6 hydrogens there. So this would be in one area, these 6 would be in one signal. Like 2 to 6, also same as 1 to 3. So it will give you as a ratio. Okay. And then the splitting. How do we observe this splitting and how many peaks it is going to split? Now this is CH3CHCl2. 1 hydrogen in one area, 3 hydrogens on one area. N is the number of equivalent protons on adjacent carbons that are not equivalent to the protons that produce the signal. So let's see. If you expand this molecule, CH3, and then you have CHCl, Cl, and this is 1 hydrogen would be in one area, and then the other 3 hydrogens would be in another area. And since the single hydrogen is close to 2 chlorine, it would be more de-shielded. So this would be 1 hydrogen. This would be 1 hydrogen, and then this would be 6 hydrogen, would be more shielded, right, close to 0. And ratio is 1 to 6 hydrogens. Okay. Now we're going to look at this carbon. This carbon, let's say this is A, carbon A, or hydrogen A, and these are all B hydrogens. Now hydrogen, attach hydrogen A next to the, so this is the hydrogen A, it's attached to this carbon, and the adjacent carbon is B, has 3 hydrogens. Okay, so hydrogen A is going to split due to the 3 hydrogens on carbon B like N plus 1. N is the number of hydrogens on the adjacent carbon. Now there are 3 hydrogens on the adjacent carbon to carbon A. So 3 plus 1 would be 4. So that 1 hydrogen over here will split to 4 peaks. And so you can see here 1, 2, 3, 4. There are 4 peaks. Okay, so we call it as a quartet. And then the 3 hydrogens on carbon B is going to split due to 1 hydrogen on carbon A. Now it again going to split as N plus 1. N is the number of hydrogens on carbon A, that's 1 plus 1. And then the 3 hydrogens will split to a doublet, split to 2 due to hydrogen on carbon A. So N is the number of equivalent protons on adjacent carbons that are not equivalent to the protons that are being produce the signal. Okay, N is the number of equivalent protons on adjacent carbons that are not equivalent to the protons that produce the signal. Always we're going to look at the N plus 1 for the adjacent carbons hydrogens. Now in this one, how many signals would you see in this case? Let's say this is our NMR axis. 3 hydrogens in the same environment, 2 hydrogens on the same environment, and C would be on a same environment. So 3, 2, 3. If this is our 0, excuse me, where is the reference point? Where do you think A would appear? Is it closer to 0? That is upfield or downfield? That's going to be upfield, right? A with 3 hydrogens. And then what about B? After A, we will see B because B is closer to a carbonyl group and a carbon. So B would have 2 hydrogens. And then the C is directly attached to oxygen. Oxygen is more electron withdrawing compared to this carbonyl group. So as a result, CH3 group directly attached to oxygen would be more de-shielded. So C. And their ratios would be, this would be ratio 2, 3, 3. So basically we will see 3 signals, but how are they going to split? Now let's look at A. If I expand this CH, okay, these A hydrogens, these are the A hydrogens, B hydrogens, and then the C hydrogens. Excuse me. Now there are 3 hydrogens on carbon A. That is directly attached to carbon that carrying 2 hydrogens. So A hydrogens are going to split N plus 1 due to the hydrogens on the carbon B. So there are 2 hydrogens on carbon B. So 2 plus 1, 3. We call it as a triplet. So the A hydrogens, so these are your A hydrogens, are going to split to a triplet. A is a triplet. Now what about B? B hydrogens, there are 2 hydrogens and they are adjacent to carbon that is carrying hydrogen A. There are 3 hydrogens. So that would split N plus 1. There are 3 hydrogens on carbon A. So 3 plus 1 is 4, that called a quartet. So the B hydrogens. So these B hydrogens that is on carbon B going to split due to these 3 hydrogens. N plus 1, 3 plus 1, 4. It's a quartet. And then we have C hydrogens. So these are the C hydrogens. They are all chemically equivalent. There is no carbon next to that C carbon C. It's next to oxygen. It doesn't split through oxygen. It only splits through carbon. So because of that, there's nothing next to the carbon C that would help those hydrogen to split. So it's going to remain as a singlet. Okay. That's how you observe the splitting patterns. always it is splitting through a 3-bond coupling. Okay, I can explain it a little bit more about the 3-bond coupling. Now in this molecule, so this, if you look at A is connected to carbon B. There are 2 hydrogens on carbon B. So 2 plus 1, 3. So these 3 hydrogen will be a triplet. And then the B, this carbon has 2 carbons that is carrying 5 hydrogens in 3-bond coupling. So B is a multiplet. Okay. And then the C again is going to split due to the hydrogens on B. There are 2, 2 plus 1, 3. So C is a triplet. And the D, and then the D hydrogen, if you look at here, there's 1, 2, and this carbon carries 2 hydrogens, so H would be, this hydrogen D is going to be a triplet due to these 2 hydrogens. Okay. Now the equivalent protons, they do not split each other's signals. This is methyl bromide or bromomethane. And these 3 hydrogens are chemical equivalent. And there's only one signal and these 3 hydrogens, and they are not going to split. Because of that, each compound shows one singlet in its proton NMR spectrum, because equivalent protons do not split each other's signals. Same thing in the next one. Chlorine CH2 CH2 Cl. These 4 hydrogens are chemical equivalent symmetrical molecule, and due to that it would give us only one peak without splitting. So the chemically equal hydrogens, they do not split each other. Now what causes this splitting? That we saw that you can get a doublet, and also you can see that there is a triplet, quartet, multiplet. So what is the reason behind this splitting? So CH3, so if you look at this hydrogen on this carbon, chemical shift of the signal for the methyl protons if there were no protons on the adjacent carbon. If you didn't have any hydrogens on this carbon, you would only see one peak, one singlet. But in this case, there is one hydrogen next to the methyl group. And because of that, these 3 hydrogens are going to split to a doublet, n plus 1, 1 plus 1, 2. Like this. But why? So there's going to be two peaks like that. And this is the reason for having a doublet. This is the direction of the applied field. If the magnetic field of the methine proton, this is the methine proton, is in the same direction as the applied magnetic field, it will add to the applied magnetic field. So the adjacent methyl protons will show a signal at a slightly higher frequency. And similarly, if the magnetic field of the methine proton, which is this one, is lined up against the applied magnetic field, it will subtract from the applied magnetic field. So the adjacent methyl protons will show a signal at slightly lower frequency. So 2 possibilities are there. So as a result, if you have just one hydrogen, it will split into a doublet, n plus 1. N is the number of hydrogens, adjacent hydrogen. 1 plus 1, 2. And let's say you consider the middle hydrogen. If you don't have any hydrogens on the adjacent carbon, you will have just one singlet like that. But now if you look at this hydrogen, there are 3 hydrogens on the next carbon. Chemical shift of the methine proton if there were no protons on the adjacent carbon. Now since there are 3 hydrogens, it would split into a quartet. And that would be the signal. 1 to 3 to 3 to 1 ratio. So it would split according to n plus 1. N means the number of protons on the adjacent carbon. There is 3. 3 plus 1, 4. Now this is how the ratio appears. Like 1 to 3 to 3 to 1. And this depends on how it aligns along the magnetic field. The way in which the magnetic fields of 3 protons can be aligned, these are the ways. It could appear all along the magnetic field or could be against it. Or could be 2 with and 1 against, 2 against and 1 with. So that will give us all these possibilities, and that would give us the heights of the peaks 1 to 3 to 3 to 1. Normally, splitting is observed with 3 bond coupling, meaning like if you have like this, that hydrogen, and then you have a carbon and there is a hydrogen. So how many bonds are between? 1, 2, 3. Excuse me. So normally we will see 3 bond coupling separated by no more than 3 bonds. HA and HB, over here HA and HB, split each other's signal because they are separated by 3 sigma bonds, 1, 2, 3. Now this is HA and HB. They do not split each other's signal because they are separated by 4 sigma bonds, 1, 2, 3, 4. Now again here HA, 1, 2, 3, 4. But there is a double bond. HA and HB may split each other's signal because they are separated by 4 bonds, one of which is a double bond. So in that case, you might see a splitting between HA and HB. Splitting may occur through 4 bonds if one is a double bond. Okay. Let's look at some NMR spectrums in the next section.